is Andreas Antoniou from the Netherlands. His co-authors are Frank Smits and Peter Stuyvesant, also from the Netherlands. Frank Smith is from the Waternet, the Amsterdam Water Supply Company, and Peter Stuyvesant from the KWR, the Water Cycle Research Institute of the Netherlands. Andreas, we are very interested and awaiting your speech.
Thank you, Professor Brauch. Good morning, everyone. Today I will give an overview of deep well injection and aquifer storage applications in the Netherlands from a perspective of water quality. So, artificial recharge of aquifer systems may be performed for various purposes. In the Netherlands, that's usually done in order to store. General driver for subsurface storage of water is usually an increasing demand in drinking or irrigation water in areas where the Dutch government has forced the water companies to restrict their groundwater pumping. This is usually enforced to prevent drawdowns of groundwater tables, to prevent seawater intrusion, or to restore wetlands in selected areas. On top of that, recent benchmarks in drinking water prices in the Netherlands are also pushing water supply companies to lower their costs. So aquifer storage is becoming an interesting option if operating without quality deterioration, of course. The main financial advantages consist of an increased security of the supply, a reduced well maintenance, little land occupation, reduction in costs related to water storage and evaporation losses, and during the water purification, when the treated water is stored in the subsurface, this way we can decrease the peak factor and allowing the facility to operate with a smaller capacity, the treatment facility. Now, we all know that processes like filtration, sorption, and biodegradation are responsible for the water recycling during its passage through the aquifer. The intentional use of these natural attenuation processes is referred to as natural aquifer treatment, which is responsible for various quality improvements, such as denitrification, biodegradation of organic micropollutants like chlorination byproducts and pharmaceuticals, and the removal of pathogen. So the environmental benefits, profits of these improvements are many, but most important is a reduced application of undesired chemicals, such as coagulants or active carbon, ozone, and chlorine, of course. So numerous deep well injection and aquifer storage experiments have been performed in the Netherlands since the early 70s. They mainly aimed at acquiring insights on the feasibility of recharging confined fresh aquifers with surface water via wells, and also acquiring insight on the water quality changes upon interaction of the injected water with the native groundwater and with the aquifer sediments. The target aquifers are usually composed of highly permeable sands, Miocene and Pleistocene age, which contains usually low amounts of very reactive iron sulfides, such as pyrite. Calcium carbonates are usually present in marine deposits and Pleistocene deposits, and also iron carbonates are often present in small amount, and they contain small quantities of manganese and magnesium, so we're talking about siderites and anchorites. The native groundwater is usually anoxic, calcite saturated, and sometimes it contains significant concentrations of dissolved iron, manganese, and ammonium. Upon injection of aerobic water, the water quality is mainly altered by the oxygen consumption by sedimentary electron donors, such as pyrite, sedimentary organic material, exchangeable iron, manganese, ammonium, etc. The induced acidity by these oxidation reactions is partly buffered by bicarbonates in the groundwater. If carbonates are present, though, they can dissolve, and they may release heavy metals in the water like iron, manganese. Also, the oxidation of pyrite may also lead to the mobilization of arsenic. This has been observed in the Netherlands. If oxygen is still present, this mobilized iron and manganese will further precipitate as iron hydroxides or manganese oxides. If, however, the oxygen front is lagging behind, which happens usually at larger distances from the well, then iron remains dissolved in manganese and may contaminate the abstracted water. Now, the impact on the abstracted water quality is very much scheme dependent. So in aquifer storage recovery schemes where we use a single dual purpose well for both injection and recovery, usually the initial abstracted water is of good quality, but it deteriorates gradually as the native groundwater is approaching the well. Whereas in aquifer storage transfer recovery, where we use two wells, the water quality is normally improving in time, and this is mainly because the aquifer that's between the two wells is getting less and less reactive in time. This figure depicts the generalized evolution in time of abstracted water quality in an ASTR scheme as a function of pore flushes between injection and abstraction well. No need to focus on the details, but what's important is this, the sulfate concentration that starts decreasing at some point. This is a logarithmic scale. So after 100 pore flushes, let's say, we're already decreasing, and after 400 pore flushes between the two wells, sulfate production has stopped, indicating that pyrite has stopped oxidizing or that pyrite has been leached out completely. This is also accompanied by a breakthrough of oxygen in the abstraction well, like we see here. Also, iron and manganese are decreasing, testifying as well of this decreased aquifer reactivity. However, in an ASR scheme, like I said earlier, during injection, iron and manganese gets mobilized, but if oxygen is still present, they precipitate as iron hydroxides. Whereas in this zone, between the oxygen front and the injected water front, because the oxygen always lags behind, iron and manganese remains dissolved in the water. So when recovery starts, these dissolved concentrations, they cross this zone where the iron hydroxides have formed and they get adsorbed, like you see here. But as recovery continues, the pH decreases gradually and iron and manganese remobilize, desorb again, so they may contaminate the well towards the end of the abstraction. Especially manganese is very persistent as it requires a pH above 7.5 to remain adsorbed on these surfaces. In addition to that, if we have carbonates containing manganese, they may dissolve even sooner. So the water quality may be bad at the very first stages of recovery. So the measures to prevent these contaminations are also dependent on the scheme. In ASR schemes, field observations and reactive transport modeling have pointed out to an increasing sorption capacity with subsequent injection and recovery cycles, and this is due to a gradual buildup of iron hydroxides. Moreover, if we can implement a buffer zone around the ASR well by halting recovery and restarting injection as soon as drinking water standards are exceeded. So this way we also improve the whole ASR scheme towards a higher efficiency scheme. A second way of preventing contamination is pre-treating the source water before injecting it. By using pH buffering agents, such as sodium hydroxide or sodium carbonate, we increase the alkalinity and the pH around the ASR well, preventing the carbonate dissolution due to the injection of undersaturated water or due to the oxidation reactions that I mentioned earlier. Moreover, we enhance sorption processes as both iron and manganese require high pH to be efficiently sorbed. I should mention, though, that For arsenic, being an anion, being negatively charged, increasing the pH is not a good idea because we facilitate the mobilization of arsenic. So we should look at lowering the pH if we have arsenic problems. And a third technique, which is the most radical one, I would say, is pre-treating the actual aquifer by injecting strong oxidants, such as permanganate. We tested this technique using column experiments, which simulated ASR very realistically in the lab, in an anoxic setting using real sediment samples. And we observed a very high improvement in recovery efficiency. We could almost abstract the whole water that was injected. That was due to the depletion of sedimentary electron donors due to increased oxidation. So pyrite was almost completely oxidized and deactivated. An extended precipitation of manganese oxides, which are the product of the reaction of permanganate with the various electron donors. And finally, increased pH conditions due to the proton consumption. So when permanganate reacts with pyrites, organic material, etc., protons are consumed, so the pH increases. Various experiments have also been performed in brackish aquifers and saline aquifers. In 1994, the Amsterdam water supply tested applying deep well injection to expand the existing open recharge system in the dunes in the coast close to Amsterdam in the Netherlands. Artificial injection is needed to combat overexploitation of fresh groundwater, which has been going on since the beginning of the 20th century, and which has been causing declines in groundwater tables, seawater upconing, and the disappearance of natural groundwater-dependent vegetation. So, pre-treated river water from the River Rhine was collected in this supply canal and was additionally filtered through aeolian sand, which you can see here. That was done in order to decrease the membrane filtration index, which, especially during the summertime months, increased due to high biological activity in this supply canal. So the water was filtered through aeolian sand. Then we had was a nylon fabric to separate the sand from the gravel pack. You can actually see it in this figure. And then there is the drainage system. You can also see that here. And below there was an impermeable plastic sheet to prevent the inflow of local iron-rich groundwater. So the water was injected via 4 injection wells into 2 aquifers, semi-confined aquifers at 30 and 60 meters depth. And the water was abstracted from a series of wells at 400 meters further. Now, besides the lateral movement of the stored water due to the native hydraulic gradient, which is something we should always keep in mind as we may lose our stored water if the native flow is too high, in brackish environments, there is also density differences which can cause the upward movement of the stored water, causing salinization at the lower part of the screen, which may and we may lose part of the fresh water because of the mixing in the well. So a study was recently performed in an area which is dominated by greenhouse horticulture and with a high irrigation water demand. Rainwater was harvested, collected in the greenhouse rooftops during the winter. There was a lot of rainfall. Then it was collected in the basin and then injected in the underlying aquifer for later use during the drier summer months for irrigation purposes. So the experiment aimed at reducing the freshwater losses by applying deep injection and shallow recovery using individually controlled well screens. This way, the recovery efficiency was substantially increased compared to a conventional fully penetrating well, which abstracts from the entire aquifer thickness. The efficiency was increased to 40%, I think, as opposed to only 20% that was initially. I won't stick to that. This is just a simulation using the CWAT model that shows these two scenarios. And this is my final example showing how drinking water production from brackish groundwater by reverse osmosis is also becoming an attractive technique, even in temperate climates like the Netherlands. The main drivers in this case are environmental problems like the pollution and salinization of aquifers, again water table drawdowns, and the effects of climate change, which may, for example, reduce base flows so rendering surface water less suitable for drinking water production, for example. So the injection of the waste saline concentrate into confined aquifers, which are of lower quality, like more saline, is an ideal disposal solution. 2 studies were initiated in 2007 to test this brackish water reverse osmosis concept. The concept is based on the fresh keeper approach, which what it does is it stops and reverses salinization of aquifers and water wells by intercepting the upcoming brackish water, preventing the mixing between shallow fresh water and brackish water. So if you look at this figure, this is a conventional well suffering from upconing of salt water. Instead, you can have 2 wells, a shallow one and a deeper one, both pumping at the same time. Brackish water is re-injected again in the deeper saline aquifers, no problem. And this well can go longer before upconing, before having to stop production due to upconing. The fresh keeper approach can be combined also with reverse osmosis to increase production. Again, the saline concentrate is re-injected in the deep aquifer, so no problem again. And this finally is the brackish water reverse osmosis, where we only have 1 well in the brackish part of the aquifer. So we just pump brackish water. By reverse osmosis, we produce fresh water, and the salt concentrate is re-injected. And we see that simultaneous abstraction of upper fresh and lower brackish groundwater leads to a lowering of this fresh and brackish water interface, testifying that instead of lowering production, brackish water should be pumped and used. In these 2 studies, I think they managed to reach a recovery, a reverse osmosis recovery of 50 to 70% before to be able to re-inject. Otherwise, clogging issues of the injection well may become a problem. So there is a limit, of course, how far you can go with reverse osmosis. So we conclude that deep well injection and aquifer storage in both fresh and brackish aquifers is feasible. Depending on the purposes, there are different issues to deal with and different preventing measures to consider. And of course, a financial feasibility assessment should always be performed in advance, as costs may become too high and drinking or water companies may opt for more traditional solutions. Thanks for listening.